Hi folks, my name is Ms. Midha, and today we're going to focus on the following question. How do we represent sequences in functional notation? Let's go ahead and get started. All right, so here you'll notice we have 5 different sequences, and it's listing the first 5 terms for each sequence. Now, what I'm going to ask you to do is using the first 5 terms of each sequence, you're going to state if the sequence of each of these sequences is arithmetic, geometric, or neither. Once you've done that, you want to define the sequence recursively using function notation. So I'm going to ask you to pause the video and take as long as you need to complete this. That is, figuring out whether each sequence is arithmetic, geometric, or neither, and then defining the sequence recursively using function notation. So pause the video and complete that. Once you have done that, and again, take as long as you need, you're going to unpause the video and we will review. Okay, so before we go ahead and write the answers to each of these sequences, let's just do a quick review on these terms, right? What is an arithmetic sequence? What is a geometric sequence? So just a reminder, when we say this word arithmetic, what is an arithmetic sequence? Well, what happens in arithmetic sequences is that you have some value that gets repeatedly added or subtracted to the previous term. Right? So we're literally adding or subtracting some value to each term. And in a way, you can really, not in a way, you can absolutely think of arithmetic sequences as a type of linear function, right? You're adding to each term. It's like the rate of change. Now, when we're looking at geometric sequences, when you see a geometric sequence, what's happening is that you have this value, which we call the growth factor. You have this value that's being multiplied to each term. Okay, and so that when you think about that, you can think about geometric sequences almost as a type of exponential function, right? Because again, it's being multiplied. Some value is being multiplied to each term to get the next term. Okay, so now that we know that, let's just sort of go ahead and figure out whether each of these terms is arithmetic, geometric, or neither. So we're going to do that part first for all 5 of these sequences. Now, if I look at this first sequence, I can tell that for each term, I have to add 10 to get my next term, right? So I add 10 to 30 and I get 40. 40 plus 10 is 50. 50 plus 10 is 60. And 60 plus 10 is 70. Since I'm adding the same value, and that's the other thing that's really important when it comes to arithmetic versus geometric sequences, whether it's arithmetic or geometric, the same value continuously, repeatedly gets added slash subtracted or multiplied onto the preceding term. So since we are adding 10 to each term to get our next term, we can tell right away that this is an arithmetic sequence. Okay, now for number 2, or for letter B, I should say, what's happening here? Well, I can see that it's decreasing, but it definitely isn't, 80 is not being subtracted by something to get 40, and that same number is not being subtracted from 40 to get 20, right? It's not like I can do 80 minus 40 to get 40 and then 40 minus 40 to get 20. It doesn't make sense. But what I can see though is that each of these terms is being multiplied by a growth factor to get my next term. Now, what is that growth factor? Well, 80 times 1/2 gives me 40. 40 times 1/2 gives me 20. And that pattern continues, right? Every term, if I multiply it by 1/2, I'm getting that next term. So since I'm multiplying, this growth factor is being multiplied to each term to get the next one, this is telling me this is a geometric sequence. Okay, now again, if you had a hard time seeing that it's being multiplied by 1/2, you may have noticed that each of the next term is half of the preceding term. That's the same idea as multiplying by 1/2. Okay, now what about the third one, letter C? C also looks like it's being multiplied by a specific value each time, right? 1 times 2 gives me 2. 2 times 2 gives me 4. 4 times 2 gives me 8. And this pattern continues. So right away I can tell, okay, this is a geometric sequence. All right, what about letter D? 1 to 1/2 to 1/4. Okay, looks again, there's definitely a growth factor here. This value, 1/2, it's being multiplied to each term to get my next term, right? 1/2 times 1/2 is 1/4. 1/4 times 1/2 is 1/8. 1/8 times 1/2 is in fact 1/16. So here is another example of a geometric sequence. Okay, now what about this last one? This last one is decreasing, Doesn't look like it's being multiplied by some value to get the next term, but it does look like it's being subtracted. So 20 minus what gives me 13? Well, 20 minus 7 gives me 13. And again, if I take away 7 from 13, I get 6. 6 minus 7 gives me -1. -1 minus 7 gives me -8. So this tells me this is an arithmetic sequence. Okay, now that we figured out what each of these sequences are in terms of arithmetic or geometric, now we can start figuring out how to define each of these sequences recursively using function notation. Now, what do we mean by this? When we're using this term function, we're using this term recursively, right? What is a recursive definition? Well, recursive definition, it describes a repeated or recurring process for getting the values of our sequence. Now, our first sequence, we're going to call our first sequence A, just because it is the first sequence in our on our paper right here. And so we'll just use that letter to call our first function A. Okay, so again, recursive definition describes a repeated or recurring process for getting the values of, in this case, A, function A. Now, a couple of things to keep in mind, right? How do we come up with our equation? Now, first of all, this is our function A. And so we know that the beginning, since we're using function notation, we know the beginning of this equation is going to be written as A of n. So how do we come up with our equation for A of n? Well, we need to focus on how to reason about in terms of the previous step or in terms of the previous term to get our A of n. And so what does that mean? Well, it's really saying if A of n is our term that we're looking at, what is the previous term? Well, that's going to be A of n minus 1. Okay, now since this is an arithmetic sequence, we know we have to add n to the end of this equation. Okay, so that's essentially how we can start to set up our recursive definition for our sequences. Okay, one other thing to note, what is n? Right, what is n? Well, n, it's essentially an integer, right? N is an integer, and it's really sort of helping us determine what term we are looking at in our sequence. So there's two other pieces that we need when we're looking at a recursive definition, right? We have to look at what value to start at and what values n can be. Those are the two very other important pieces to helping us write this definition. So in this case, our first value in our sequence, we would call this A of 1. Okay, now here, what is A of 1? Well, A of 1 is our first term in our sequence. So that's going to be 30. Okay, that's going to help us with determining what to write in the rest of our equation, if you will. Okay, so now two very, very other important pieces of info that we need. First of all, what is this value of n going to be right here? Just highlighted that right now. What is that value going to be? Well, that value is based upon what this sequence is, what value is being added to each term in this sequence, right? And what value was being added? Well, we can tell right here that the number 10 was being added every single time. So what we can do now is that instead of writing plus n, we can actually go ahead and write plus 10. Okay, now we are not done yet. There's one more very important piece of information that we need to add to this. We need to determine essentially, like, you know, we know that n was that integer in that part of the equation, right? N was that 10. We know that that was being left off. We also need to know, where is this n in our A of n? Where is this starting, right? It's because it's not going to be starting at 1. We already know that A of 1 is 30. So when we're figuring this out, what we also need to write here is where n is going to start. So we can say that our equation, first of all, our equation is in fact going to be A of n equals A of n minus 1 plus 10, where n is greater than or equal to 2. So that's how you would write this recursive definition for our first sequence. Okay, now I'm going to go ahead and answer the other ones using the same idea. And again, I'm going to change the names of each of these functions according to what is essentially what the sequence is already called. So with the first one, I know that my function is going to be called b. And I'm going to actually start this off first by saying what b of 1 is, right? We always want to really just sort of start every one of these recursive definitions with that. So we know b of 1 is 80 because that is our first term in our sequence. And we know that we're going to start this out by writing b of n, right, equals b of n minus 1, the preceding term, b of n minus 1. Now, instead of adding a number to each one of these, since we know it's a geometric sequence, we know we're going to be multiplying this to our growth factor. And what was our growth factor here? It was 1/2. Okay, what's the other piece of information we need here? We need to make sure we also include the fact that n is greater than or equal to 2. All right, same idea for the third one. We know this is c, our function c. We know c of 1 is equal to 1. And we know our function, there we go. We know that our sequence, our recursive definition is going to be written as c of n is equal to c of n minus 1. Again, what is this going to be multiplied by? Our growth factor of 2. So we know it's c of n equals c of n minus 1 times 2, where a, once again, is greater than or equal to 2. Okay, next one. Hopefully you're seeing the same idea happening for each one of these and it's starting to make more sense. We have d of 1 is equal to 1. D of n is equal to d of n minus 1. What was the growth factor? Well, times 1/2, so we can write that, where n is greater than or equal to 2. And then finally, we have e as our name of our function. So e of 1 is equal to 20. And e of n is equal to e of n minus 1. Now, again, this is an arithmetic sequence, so we need to subtract 7 here, or plus -7, where n is greater than or equal to 2. So that is how you write a recursive definition using function notation, right? It says the same format, whether it's arithmetic or geometric, in terms of stating what your first term is, right? B of 1 is equal to 80 in the case of our second sequence here. And then always thinking of it, or I wouldn't say thinking of it, but always sort of reasoning about in terms of the previous step in order to determine our equation for that sequence, right? The other big difference is determining, well, am I going to add an integer or am I going to multiply an integer after stating my sequence of a of n minus 1 if we were looking at that first sequence. All right, and that's about it. And remember, just when you're looking at arithmetic sequences versus geometric sequences, we also looked at the difference between those two.